Now that we know how the cores are cut, boxed, and preserved, let's see what happens here at the laboratory where they are analyzed. In this unit, we shall see how the cores are described and sampled, and how what we refer to as conventional core analysis is carried out. Later, in the next unit, we shall look at special core analysis.
Once the entire core reaches the laboratory, it is placed in order of depth on a layout table and removed from its wrapping. It is then refitted, and if a core description was not made in the field, one is made at this point in time. Then the natural gamma ray activity of the core is recorded using a radioactive pickup device. The core is logged by passing it through a lead tunnel containing a gamma ray counter. The record obtained is often referred to as the core gamma log. This data, which is often digitized, is used to identify core lithology and to make depth correlation with downhole logs. By comparing the core gamma log seen here on the right with the wireline log on the left, it is possible to correct any depth discrepancies.
The largest depth discrepancy that we have seen between core depth and log depth was 180 feet, or about 55 meters. Core depths are usually adjusted to log depths.
The core is also usually color photographed, either as a whole core or in slabbed sections. The photographs are taken under both natural and ultraviolet light. Ultraviolet light can reveal the presence of hydrocarbons.
Color photos of cores allow the several partners in a well to examine the many features of a core at their desks. This means that they don't have to go to the inconvenience of visiting the core warehouse.
The next step is the recording of a detailed lithological description of the core. This description usually includes the rock type, that is, whether a clastic or carbonate, its color, and whether the color is constant, mottled, or banded, its textural characteristics, which include an indication of grain size, as well as such major characteristics as the presence of lamination, shale, or fossils, and such minor characteristics as the presence of mica, pyrite, or glauconite. Its hardness, that is, its degree of consolidation and cementation. And finally, the presence and color of any oil staining. Because we are in the business of finding hydrocarbons, we look to the color and fluorescence of the cuttings during drilling, the core itself, and the color of the oil cut in a solvent, to give us a direct indication of the presence of hydrocarbons. A typical description might read, sandstone, buff, fine-grained, shaly and laminated, friable, blue-white uniform fluorescence. The report prepared as part of a conventional core analysis usually includes a lithological description. The description is often given in abbreviated form, as we see here. In the appendix to your manual, you will find a complete list of typical abbreviations.
Once the cores have been described and photographed, samples are selected for analysis.
3 basic sizes of core samples are used for testing. The plug size sample, which is cut selectively from the full core. The full diameter core sample, which is used to analyze rocks with complex lithologies such as heterogeneous carbonates, vugular formations, and fractured zones where plug sampling is unsuitable. And, finally, the plug size samples that are obtained from sidewall percussion or drilling devices. Let's first say a few words about the way in which representative samples are selected for analysis, and then discuss the various tests that are run in the laboratory to obtain both engineering and geological data.
The objective of plug sampling is to obtain a series of samples that are representative of the whole core. The plug should be cut parallel to the bedding plane for horizontal flow tests and perpendicular to them for vertical flow tests. The plug itself is typically 1 inch or 2.5 centimeters in diameter and 4 inches or 10 centimeters in length. It is trimmed on its edges to remove regions where filtrate invasion and mud solids exist.
Whole core samples, generally 6 inches or 15 centimeters long, are selected from each foot of core. The irregular ends of the sample are usually clipped with a diamond saw.
All sidewall samples obtained in the field except shale samples are analyzed in the laboratory. This means that the selection of samples is made by the operator before the wireline tool is run in the hole.
The three types of samples just mentioned are the most widely used, but there are others. And in Chapter 4 of your manual, we have pointed out how cores delivered to the lab within the various types of sleeves or core barrels are sampled for analysis.
There are a number of ways available to clean the fluids from the sample. The more popular are the Dean-Stark or Soxhlet extraction methods. In this Dean-Stark apparatus, the sample is placed in a jar with a solvent, usually toluene, placed in a flask below. The boiling point of the solvent must be greater than that of water. The solvent is heated, rises, and passes through a condenser. The condensed solvent then drips onto the core sample, heating it and extracting its fluids. As the sample reaches higher temperatures, its liquids vaporize and move upward with the toluene, where they in turn pass through condensing tubes, condense, and fall back into a calibrated tube. Oil dissolves in the toluene. Because the solvent is lighter than the water falls to the bottom of the tube and only the condensed solvent spills over the top and falls to the flask below. When successive readings indicate that no further water has been recovered from the sample, it is transferred to the core cleaning cells, where any remaining oil is recovered under toluene and CO2 pressure washes. When it is considered clean of reservoir fluids, it is ready for drying. We shall discuss this method in greater detail later.
Once the samples are clean, they are dried in an oven to remove the toluene. Stable rocks are dried at temperatures up to 240 degrees Fahrenheit or 115 degrees Celsius. Clay-bearing rocks are dried in a humidity drying oven set at a relative humidity of 45% and a maximum temperature of 145 degrees Fahrenheit or 64 degrees Celsius.
The drying time depends on the permeability of the sample. High permeability rocks may need only 24 hours to dry. Tight rocks require 48 hours or longer. The cleaned and dried samples are now ready for us to measure the first two basic rock properties, porosity and permeability.
Porosity, we remember, is a measure of the reservoir storage capacity. It is defined as the void or pore volume divided by its bulk volume. It enters equations as a fraction, but is usually reported as a percent. It ranges in magnitude from 10 to 40% in sandstones and 5 to 25% in limestones and dolomites. The porosity is defined as the pore volume divided by the bulk volume. But the pore volume is equal to the bulk volume minus the grain volume, and so we have a second relationship for porosity. And if we redefine the bulk volume as the pore volume plus the grain volume, we have a third definition of porosity. All this tells us that if we measure any two of these three properties, we can calculate porosity. We may do so by using either the Boyle's law technique or the summation of fluids technique. Let's discuss each briefly. In the Boyle's law technique, the pore volume or grain volume of the sample are measured by the compression of gas, usually helium, into the pores, or the expansion of gas from the pores. By the careful measurement or control of pressures and volumes, the pore volume may be calculated using Boyle's law. The bulk volume is also usually measured. This may be done by physically measuring it with a caliper, but the error in the estimation may be high, so other techniques are used. One method often used is to place the sample in a reservoir of mercury, as we see the operator doing here for a plug sample, and measuring the volume of mercury displaced by the sample. The mercury should not penetrate the sample at the low pressures of the test. This then gives us a measure of bulk volume, and with our known value of grain or pore volume, we can calculate the effective porosity of the sample quite easily.
Don't rush samples through analysis without adequate time for drying. The results may lead to porosity values that are 10 to 15% too low.
The second method of measuring porosity is the summation of fluids technique. With this technique, we measure the gas, oil, and water volume in the pore space of a fresh core and sum them to yield the pore volume. The bulk volume is calculated, as we mentioned earlier, using the mercury or other displacement method. Measuring porosity in this way requires measurements on two portions of a core sample. One portion is approximately 100 grams in weight, the other about 30 grams. The 30-gram sample is used to estimate the gas pore volume, the 100-gram sample to estimate both oil and water pore volume. Let's begin with the gas pore volume. The sample is weighed and then its bulk volume is measured by mercury displacement. The sample is then placed in a mercury chamber where its pressure is increased to 1,000 psi or 6,895 kilopascals. At this pressure, mercury enters the sample and allows us to calculate the relative pore volume occupied by gas. The larger sample is used for measuring oil and water pore volumes in a high-temperature retort. The sample is crushed into small fragments, weighed, and placed into a sample holder and capped. The holder is placed in an oven with its lower end connected to a calibrated receiving tube. The temperature is raised in two stages. First, to 350 degrees Fahrenheit or 175 degrees Celsius for 30 to 40 minutes to vaporize the water. And then to 1200 degrees Fahrenheit or 650 degrees Celsius for 45 minutes to vaporize the oil. In time, the fluids build up pressure in the holder and pass downward through a water bath and collect in the graduated receiving tube. Some oil is lost to coking and cracking during retorting, and so a correction must be applied to estimate the oil saturation. We must also apply a correction for the water volume collected to distinguish pore water from water of crystallization. The appropriate procedures are in your manual.
With the bulk volume and measured value of gas, oil, and water known, calculation of porosity is straightforward. We should point out that the accuracy of these measurements is good, say plus or minus 0.5% porosity, if the proper procedures are observed.
You're right for well-cemented rocks, but not for unconsolidated samples. The measured porosity could be 20% too high. Why? Because you're not considering confining pressures. For unconsolidated samples, the porosity should be measured under confining pressures, equivalent to in situ stresses.
Permeability is a measure of the flow capacity of the rock sample. Absolute permeability is its value when a single fluid completely saturates the sample. Its value is measured by placing the sample in a holder or sleeve and flowing a fluid of known viscosity, usually air, through the carefully measured sample. The pressure differentials and flow rates are measured, and the permeability is calculated from Darcy's law. Here we see the test apparatus. In this case, the whole core is mounted vertically in the core holder, and the core sleeve is raised around it. Measurements are made at several different flow rates, and the permeability reported as permeability to air. It has been observed that when a gas is used in the test, the permeability is different for each different flowing pressure. This occurs because gas, at low pressures, slips through the pores with little friction loss. At high pressures, the calculated permeability approaches that for liquid. This is known as the Klinkenberg effect. To obtain the correct permeability, we normally measure air permeability at different average pressures, plot their values versus the reciprocal of pressure as we see here, and extrapolate the line joining the points to the left axis, a point that represents a very high pressure. This is referred to as Klinkenberg permeability and is equivalent to the liquid permeability of the sample.
Here is an example of the permeability data reported for a conventional test. Often a simple air permeability value, as we see here, is reported for each sample without a Klinkenberg correction being made. Here you know what value is given in your core report. Measuring horizontal permeabilities on a full diameter core is performed by placing two screens on opposite sides of the core. Impermeable rubber discs are placed on the ends. The core and screens are then put into a Hassler sleeve. The sleeve and ends are then collapsed by the confining pressure around the core within the test apparatus. The horizontal permeability value is then measured. The core is rotated 90 degrees within the screens, and a second horizontal measured. If one or more fractures are present, the maximum value is measured parallel to the strike of the fracture. The data is reported with the maximum value referred to as Kmax and the lower value referred to as K90 degrees. The vertical permeability is by removing the screens and rubber end pieces and measuring flow conditions vertically in the core. These data are also given in the core report, as we see here.
Full diameter cores are easy. Trying to obtain accurate measurements of permeability in sidewall cores is in most cases difficult. We usually estimate their values from previously developed correlations.
Just as we mentioned for porosity, investigators have found that overburden pressure and reservoir temperature conditions have an important effect on permeability measurements. In laboratory experiments, investigators have found that when they bring cores to simulated conditions, they've observed permeability reduction from as low as 7 to as high as 100%. The higher values, of course, are for unconsolidated formations. Because of these potential errors, permeability measurements are now often made under simulated reservoir conditions. Let's now move on to the third conventional test, the measurement of fluid saturations.
There are two procedures normally used for measuring fluid saturations in the cores after they arrive in the laboratory: the retort distillation method and the Dean-Stark method that we mentioned earlier. Let's begin with the retort distillation method. The apparatus used is the same one we discussed for measuring porosity using the summation of fluids technique. The sample is first weighed, and its bulk volume is then measured or calculated. The sample is placed into the metal holder and the top screwed on. The metal holder is placed in the retort oven, and a calibrated receiving tube is connected to the hollow stem, which projects downward from the holder. The oven is turned on. Fluids vaporize, build pressure in the sample holder, and are forced downward. They pass through a condenser located below the oven but hidden from our view, and the condensed fluids collect in the receiving tube. Oven temperatures, increased in 2 stages to a maximum of 1200 degrees Fahrenheit or 650 degrees Celsius, cause the liquids to vaporize and the oil to be distilled. The water volume is corrected for any water of hydration or crystallization that may have been recovered, and the oil volume is corrected using a retort correction curve, which accounts for oil coking and cracking at high temperatures. These correction methods are explained in your manual.
Knowing the weight and porosity of the sample, together with the volumes and specific gravities of the oil and water collected in the calibrated tubes, it is a simple calculation to estimate the oil and water saturations. Incidentally, this method may be used for full diameter samples, but in that case, we usually pull a vacuum on the system and limit the temperature to 450 degrees Fahrenheit or 230 degrees Celsius. At this temperature, the sample is not destroyed. At the higher temperature, it is.
The Dean-Stark method we mentioned earlier when we discussed the cleaning of cores. To calculate fluid saturations, the fresh core is first weighed and then placed within the Dean-Stark apparatus, suspended above a flask containing solvent such as toluene. The toluene is heated, vaporizes, and rises in the condensing tube, where it condenses and falls onto the calibrated tube. When the tube fills, the spillover drips back onto the sample, warm. Ultimately, the sample reaches the boiling point of water. Water then vaporizes, moves upward, condenses, and is also collected in the graduated tube. Because it is more dense than toluene, it remains in the bottom of the tube, where its volume may be measured.
Some oil is recovered from the sample using this procedure. Often additional processing is required to remove all the oil. Typically, the samples are removed from the Dean-Stark apparatus, placed in core cleaning cells where, at elevated temperatures, they are exposed to repeated pressure cycles of a solvent mixture of toluene and CO2. First, the solvent is injected into the sample at elevated pressures. The pressure is released, and the solvent, carrying with it dissolved oil, is exuded from the sample. From time to time, the samples are removed from the oven and checked under ultraviolet light to see if all the oil has been removed. If not, they go back until it has.
The Dean-Stark method allows the sample to be used later for porosity and permeability measurements, but keep in mind that solid and vaporized water remain in the so the calculated values of water saturation, porosity, and permeability may be low.
An alternative method for cleaning the sample is to use chlorothene or benzene in the Dean-Stark apparatus. After cleaning, the sample is often saturated with to remove any salt precipitates from the brine. After all the oil and water is recovered, the sample is placed in an oven to dry. Once dry of the solvent, it is then weighed. It is then a simple matter to calculate the oil and water saturations.
The oil saturation calculated for a plug sample using the Dean-Stark method relies heavily on the difference in weight of the sample before and after processing. If a few sand grains are lost during the test, the weight measured after drying is too low, and the calculated oil saturation will be too high, so be careful.
The oil and water saturations, usually given on a percent of pore volume basis, are also reported on the standard core analysis report as we see here. The difference between 100 and these two values is the percentage of pore space filled with gas at the time of the analysis. In the next column, we see the recorded grain density of the sample. This is easily calculated once we know the dry weight of the sample, its bulk volume, and porosity. These grain density values are of special importance in the calculation of porosity from downhole logs.
With the widespread availability of the computer and plotting routines, it is now possible to prepare continuous plots of the core analysis data versus depth, where interpolations are made between data points as we see here. To calculate cross-plots of data such as a permeability frequency distribution and cumulative frequency distribution. A plot of permeability versus porosity data points with the best straight line drawn between them. Or a plot of permeability versus water saturations as we see here. Are you wondering about the points at the top? At high permeability and high water saturation? Turns out they are tight formations that are naturally fractured. Your imagination will lead you to many more data plots that can be made. Because of the sparsity of data points for sidewall cores, reports for these samples are usually simply tabulated and not given as continuous plots.
Enough for now, you say. We agree. We have seen in this unit how the important conventional core data for porosity, permeability, and fluid saturations are measured and reported in both tabular and graphical form. In the next unit, we shall discuss a few more important core tests. But for now, please take a moment to work exercises 4 and 5 in your manual. In this, the last unit in the module, we shall discuss two major areas: the complementary core analysis information that is gathered on a core and the important special core analysis that are run on core samples in order to provide special information to the engineer or the geologist.
There are a number of observations recorded or measurements made on cores, which we shall refer to as complementary core analysis information. We've already discussed some of them in Unit 2, others we shall mention briefly here. One that we mentioned in the early part of Unit 2 was the recording of the lithology, texture, and fluorescence of the core soon after it reaches the laboratory. This provides a better understanding of the depositional environment of the interval cord, its response to downhole logs, and the influence of rock texture on porosity, permeability, and water saturation.
We also pointed out that the core is usually photographed under both natural and ultraviolet light. A photographic record is invaluable as a means of conveying visual information to others and for later use when reservoir studies are undertaken.
The core gamma log, taken of the core shortly after it arrives in the lab, is another piece of complementary core information. Recording the natural gamma radiation of the core may be used for comparison with the visual assessment of the core lithology and for log correlation purposes.
The cation exchange capacity, or CEC, another complementary core test, allows us to calculate the true water saturation in clay-bearing formations. The CEC is a function of the clay type and amount present, as well as the porosity, and may be determined using wet chemistry techniques. On the left, we see the sample being stirred. In the center, the titration unit, and on the right, a pH meter. If we ignore the cation exchange capacity of clay-bearing formations, we may calculate water saturations from logs which are too high, thus causing us to overlook potentially productive formations or understate oil in place from producing zones.
Grain size distribution is another important piece of core information used not only as an indicator of reservoir quality and depositional environment, but also for sizing gravel packs to prevent sand flow into the well bore. There are several methods available for measuring grain size distribution. One involves the sieving of a disaggregated core sample through a nest of various size screens, as we see here. Once the sample has been separated, the various trays are weighed and the results recorded. Whatever the method used, the data is recorded and usually summarized in a statistical form, as we see here, where the cumulative grain size distributions of a gray wax sand and shaly sand are compared.
Another important observation that can be made on recovered cores is the study of natural fractures. To describe the fracture pattern properly, a specially orientated core should be taken. A core that has been taken so that its orientation is known is shown here. Note the vertical offsetting grooves that are cut into the core while it was being cut. These allow us to specify the original orientation of the core in the hole. When the core is placed in a core holder with the orientation lines properly aligned, fracture strike and dip can be measured. In this case, with a measuring arm that records the data automatically by a personal computer. The data from a number of fracture measurements are usually printed out in the form of a rose diagram, which gives the dominant fracture strike or compass orientation, which, as we see for this formation, is approximately northeast and southwest, and in the form of a histogram for the distribution of fracture dip. In this case, the fracture dip clusters around 45 to 50 degrees. There are a number of immediate applications for this data, including the location of wells to take advantage of fracture permeability, the correlation fracture finding logs, the design of well completion and stimulation programs, and as input to simulation models.
We're finding that most hard rock formations are naturally fractured and that a whole core analysis under net overburden stress conditions and a careful evaluation of the fracture system must be undertaken to provide meaningful results.
Of course, measurement of directional permeability at greater intervals than 90 degrees is also possible and is often done where the prediction of fluid movements is important. Just as for fractures, the data is usually reported in the form of a rose diagram, as we see here for each sample. The sample frequency is 30 degrees. Note how the permeability data correlates with the fracture strike data. This information is important in planning fluid injection programs.
There are just a few more tests, like the ones we just mentioned, that are carried out on a core sample to provide additional information about core properties. They are discussed at the end of Section 7 in your manual. Now let's go on to the special core analysis tests. There are three major ones to be discussed: capillary pressure, electrical properties of the core, and relative permeability.
It is a well-known fact that a capillary pressure exists across a fluid interface when the fluids are contained within a capillary environment. The height of rise of fluids in a capillary above the free surface is proportional to the capillary pressure, which, in turn, is inversely proportional to the radius of the capillary. Here we see that water rises higher in smaller diameter capillaries because the capillary pressure is higher in smaller tubes. This is true provided the capillaries are water wet. The same principle of physics exists in a porous medium, because our pore system is a capillary system. Thus, if we plot the capillary pressure versus water saturation for a rock sample, we can learn something about its pore size distribution and ability of hydrocarbons to migrate into the formation that it represents. Because capillary pressure is proportional to the height of rise above the water level, we can make an appropriate conversion to the vertical axis. From capillary pressure to height. For a clean, medium-grained water-wet miocene sand or a vuggy carbonate, the water saturation is easily displaced by the invading hydrocarbons, and the irreducible water saturation drops to as low as 12% at a low capillary pressure. For a fine-grained, shaly miocene sand, the water saturation is only reduced to 30%, even at a higher capillary pressure. And in the extreme, for a very tight sand, the water saturation commonly does not drop below 85%, even at a moderate capillary pressure. We should point out that it is now possible to expose samples to very high capillary pressures, which will drive the water saturation to lower values. Knowing the capillary pressure versus water saturations for our rock sample allows us to calculate the irreducible water saturation in our formation above the oil-water or gas-water contact. It also allows us to estimate the vertical height of the oil-water or gas-water transition zone. As we see here, small for the clean sand, large for the tight sand.
Measured capillary pressure data then allows us to estimate the initial water and hydrocarbon saturation distributions in the formation.
There are three methods for measuring capillary pressure on a core sample. One method involves the use of a centrifuge. First, the calibrated receiving tube is added to the holder. Above this, the brine-saturated plug sample is placed in the sample cup, which is attached to the receiving tube with an O-ring and sealed into the holder. The multi-stage holder is then inserted into the centrifuge, in this case an ultracentrifuge, and it is turned on. The water entering the calibrated tube at successively higher speeds is recorded, and a conversion to capillary pressure is made.
Because the ultracentrifuge now goes to 20,000 Gs, it permits us to determine imbibition and drainage capillary pressure data, even in low-quality rocks, with reservoir fluids, a reservoir temperature, and axial stress conditions.
A second method for measuring capillary pressure, one that has been popular for many years, is the mercury injection technique. A core sample is placed in a pressure-retaining holder. A vacuum is placed on the sample, and then mercury is pumped into the sample at progressively higher pressures. Many data points are obtained, but the sample is destroyed in the process. At low pressures, the large pores are filled with mercury. At high pressures, the smaller pores are filled. With appropriate calculations, we obtain what we need: a plot of capillary pressure or height above the oil-water contact versus water saturation, and from that, the initial connate water saturation distribution.
This information is also important in measuring pore throat size distribution of our sample. Pore throat information is especially important when considering enhanced oil recovery fluids. The next special core test is that of measuring the electrical properties of the core sample. This data is of special importance in correlating logs to formation porosity and to hydrocarbon content.
There are three measurements of electrical resistivity that are of interest to us: the resistivity of the formation brine, R sub W, that of the porous medium when it is 100% saturated with the brine, R sub O, and finally, the resistivity of the porous medium when it is saturated with the brine and a hydrocarbon, R sub T. The test is normally run on plug samples at various levels of water saturation. In this test apparatus, we can see that several samples can be analyzed at one time. They are placed in a platinum-titanium holder and allow the test to be conducted at reservoir conditions of temperature, overburden pressure, and pore pressure. By measuring the length and cross-sectional area of the sample and recording its electrical resistance, it is a simple matter to calculate its resistivity. Once the resistivity measurements are made, the results are plotted as two quotients. The first quotient is referred to as the formation factor F and is the ratio of R sub O divided by R sub W. The second quotient is the resistivity index Ri and is the ratio of R sub T divided by R sub O. For a given brine, we have a pretty good idea that the resistivity of the brine-saturated porous medium, and therefore F, will increase with decreasing porosity. And Archie has suggested that a log-log plot of F versus porosity will yield a straight line with a negative slope of magnitude 2. The slope M is called the cementation factor. Our data point should fall on this line. However, conductive solids such as clays will yield a lower value F for the same porosity, and measuring F at a high overburden pressure will give a higher value for the same porosity. A range of values for M, then, has been found to exist, and it is for this reason that laboratory measured values of F are needed for correlating log-derived values of porosity, values which depend upon measurements of resistivity. When we look at the terms in the resistivity index, we see that the only difference in the measurements is the level of water saturation. Because it is the ions in the brine that conduct electricity and not the hydrocarbons, the higher the water saturation, the lower the resistivity index. Once again, a log-log plot, this time Ri versus the water saturation S sub W, yields a straight line. This line is normally expected to have a negative slope, N, approximately equal to 2. The quantity N is referred to as the saturation exponent, but the value of Ri for a given saturation may fall below the line if clays are present or above the line if overburden pressure is applied during the test. A range of values of N then is possible, and for this reason it is important that laboratory-derived values be obtained to correlate logs that yield water and hydrocarbon saturation values.
If you use the wrong cementation or saturation exponent, you may estimate a water saturation from logs of, say, 100%, when it is really 45%, or a porosity of 10%, that is really 21%. This could lead to a poor evaluation of a good well.
In addition to the measurement of electrical resistivity of our rock samples, we often measure its acoustic velocity, because a good correlation normally exists between acoustic velocity and porosity.
The test apparatus and procedure are similar to those used to measure resistivity. In this case, the acoustical velocity of a whole core sample, rather than 4 plug samples, is being prepared for measurement.
Now let's go on to the last of our special core analysis tests, relative permeability.
We remember from PE 501 and GL 302 that relative permeability is a direct measure of the ability of the porous system to conduct one fluid when more than one is present. It is defined as the effective permeability to a specific fluid, say oil, water, or gas, divided by some base permeability. Until about 1973, the base permeability was the absolute or air permeability, but now it is normally the oil or gas permeability at connate water saturation. The range of relative permeability, then, is from 0 to 1, and it is a function of, say, water saturation, which has limits of 0 to 100%. Now we can plot relative permeability to either oil and water or gas and water as a function of water saturation. Let's select gas and water. Under normal reservoir conditions, we cannot reduce the water saturation below its critical or irreducible water saturation, S sub Wc. Nor can we increase the water saturation beyond that represented by the critical or irreducible gas saturation, S sub Gc. Relative permeability, then, is defined between these two limits. In order to measure relative permeability in this example, we must either increase or decrease the water saturation in our core sample during analysis. If we increase the wetting phase saturation, we refer to the resulting curves as imbibition relative permeability curves. If we decrease the wetting phase saturation, the curves are referred to as drainage curves. If the test core sample is water wet and we increase water saturation, we obtain imbibition curves. If we begin with the sample 100% water saturated and reduce the water saturation, we obtain drainage curves. Note that the curves are different, especially the relative permeability to gas curves. We see that if we are going to undertake a water flood, we should be sure to measure and use imbibition relative permeability curves for a water-wet reservoir rock. If instead of gas, the sample is saturated with oil, we will measure the relative permeabilities to oil and water. Here on the left is a typical set of oil-water imbibition curves for a strongly water-wet rock, and on the right, a set for a strongly oil-wet rock. We see the shift caused by a change in wettability.
The accuracy of relative permeability curves, then, depends on the wettability of the sample in the laboratory being the same as it was in the formation, and then having the laboratory data obtained according to the process we propose for the reservoir, imbibition or drainage.
There are two major ways to measure relative permeability in the laboratory. In the steady-state method, the core sample is placed in a sleeve, which maintains a seal by the application of pressure, and mounted with a mixing head at the inlet end. A second head or separator may exist at the outlet end. Two fluids, in this case brine and oil, are injected simultaneously at low flow rates into the inlet end. The saturation of one of the fluids is increased slowly. Saturation increase is monitored by measuring the weight gain or loss in the sample. By X-ray techniques or by material balance methods, the flow rates at the outlet end are measured and relative permeabilities are calculated. The second way of measuring relative permeability is referred to as the unsteady state method. In this procedure, a single fluid, usually water, displaces oil and water from the presaturated sample. The relative permeability curves are calculated by measuring the relative volumes of fluids injected and effluent produced over time, and then applying the Buckley-Leverett frontal advance relationships. Note that the data from the unsteady state may differ from that obtained in the steady state method. Here we see a typical system for measuring unsteady state relative permeability values, in this case, gas water values. The sample is mounted in a Hassler sleeve and then placed inside the holder. The ends are added, lines connected for the injected gas and produced fluids, and pressure is applied around the Hassler sleeve annulus. Flow rates and pressures are measured continuously during the test, which may take 24 hours or longer to complete. Often these tests are conducted under simulated reservoir conditions to be representative of actual conditions.
Core analysis has changed dramatically in the last 10 years. Now that we can run special core analysis tests at reservoir conditions of pressure and temperature, we are finding significant differences between those results and measurements made at atmospheric conditions.
There are other special core analyses that may be undertaken in order to obtain specific information, say for an enhanced recovery project, but these tests are beyond the scope of this module. We refer you to your own in-house specialists for this information. We should say a few words, though, about petrographic studies, studies that allow us to look into the pore and mineral structure of our core sample, or cuttings. There are three of major importance: thin section analysis, scanning electron microscopy, or SEM, and X-ray diffraction.
Rock samples, often after its pores are filled with a blue epoxy under pressure, are mounted and ground to a uniform thickness of 0.03 millimeters. They are then studied under a petrographic scope using both normal and polarized light. Magnification of up to 300 times is usually possible. We are then able to identify the minerals present in both the grains and pore filling, and to specify the rock texture, the nature of diagenesis, and estimate porosity. By using a point counting technique where measurements are made at, say, 100 to 300 grid points on the sample, it is possible to provide a statistical estimate of these data. Thin section analysis, unfortunately, is not a good procedure for identifying clay minerals because, except for kaolinite, they cannot be seen easily at this level of magnification.
We have found that thin section petrography is the best technique for determining rock texture, pore space distribution, and composition of framework grains. This is essential information for understanding how rocks will react during drilling, completion, and stimulation of a potentially hydrocarbon productive interval.
The scanning electron microscope does not suffer from this limitation. Magnification of up to 40,000 times is possible, and what we see is a three-dimensional view of the pore space. Here we see two gold-coated samples being placed in the sample chamber to be scanned. We can scan the sample from low to high magnification. It allows us to study both the morphology and distribution of clays, to thoroughly document rock fabric, and to observe the microporosity present in clay linings and carbonates.
X-ray diffraction is a good technique to provide quantitative estimates of rock mineral composition, both absolute and relative percentages of the various clay minerals present in the sample. A ground sample is placed on an aluminum holder, mounted in a multi-sample holder. Each sample in turn is inserted into a chamber where it is bombarded with X-rays. Certain minerals reflect the X-rays from atomic planes within the crystal lattice and yield a unique diffraction pattern. By studying the diffraction pattern for both bulk and clay minerals, we can obtain their relative composition. The composition may be recorded graphically using a plotter.
In this unit, we have covered the complementary information collected on cores, the special core analysis tests, and the petrographic studies done on our core samples. We have seen how each adds to our understanding of the reservoir rock properties. This data is especially useful in correlating logs or designing both stimulation and enhanced recovery programs. In the module itself, we have seen how coring objectives are stated, how both conventional and sidewall cores are taken, wrapped, and preserved. We've also seen how full cores and plug samples are selected, and how these samples and sidewall samples are analyzed in the laboratory. We learned that the various tests or data collected are referred to as conventional tests, complementary information, special tests, and petrographic studies. We are sure to keep the limits of the data obtained from these tests, especially the changes in wettability during recovery or the effect that imposing reservoir conditions on our sample would have on the results. We will also remember that a coring program requires careful planning.
Tell the coring contractor to contact us at least a week before coring, and we'll be happy to help with the planning.
We end this module in two ways. First, by letting you see relatively new core analysis systems developed on one hand by a group of geoscientists in Silicon Valley, and on the other by medical technologists. We will then ask you to work a few exercises.
The new core analysis system developed by the Silicon Valley geoscientists allows us to measure porosity and permeability under overburden conditions on a number of samples and prepare the reports automatically. The analysis can be done overnight if you want while you sleep. The sample measuring system is coupled to a personal computer. The operation of the system is quite interesting. Up to 14 plug samples are placed in holders and measurements begin. A sample is confined under a pre-programmed net overburden stress, and then a valve is opened allowing the helium to flow from a fixed chamber through the core sample. The pressure in the chamber drops as the helium passes through the core. By monitoring flow rates and pressures and solving the non-steady state flow equations, the porosity and permeability can be calculated at a series of average flowing pressures. The computer controls the test procedure, monitors pressures, performs the calculations, and prepares the output reports. Porosity and Klinkenberg-corrected permeability values are calculated at a series of net overburden stresses. This is an interesting application of the joining together of geoscience, repetitive testing, the silicon chip, and the personal computer. Many more such applications are sure to follow, and in fact are now in place. The second core analysis system comes from the field of medicine. Instead of using a CAT scan for the brain, it is used to observe fluid saturations and fractures in cores. This whole core sample was placed under a CAT scan and then gave us this scan of the interior of the core. Note the fracture and the different hues representing different fluid saturations. Open new developments such as these.
Now it's your turn. Please work exercises 7 through 9 in your manual. Good luck, and thanks for being with us.
This program has been sponsored in part by the following companies. IHRDC and the above-listed companies, by their sponsorship, do not in any way guarantee or represent the accuracy of the content or methods contained herein, and the user, upon using this program, thereby agrees to hold IHRDC and the sponsors jointly and severally harmless from any and all damages, including legal expenses, which may arise out of the use of this program. No portion of this video tape is reproduced without the written consent of IHRDC.